Yeah, okay, thank you. It's great to participate in this very nice workshop, and I'm very grateful to the organizers for inviting me and allowing me to speak about some recent work on Soliton friction. So this is work with Dmitry Efimkin and Viktor Gerlitsky, both of which are here. And we have heard in the two previous talks that quantum gases are a very nice environment where solitonic excitations can be created and controlled with very high precision. Of course, solitons are ubiquitous in many areas of physics, and quantum gases for the past 10, 15 years has brought us some incredible versatile platform to create and manipulate these solitonic objects. And I will talk about solitons in bosonic quantum gases, so Bose-Einstein condensates, where the condensate behaves as a soliton, as opposed to solitons in mostly Fermi gases that the two previous speakers have talked about. So the basic motivation for this work is the observation that on the one hand we have a soliton, and we have learned that the soliton can behave like a very heavy classical particle, and when placed in an optical trap it will slash back and forth with a characteristic oscillation frequency, and so it behaves very much like a heavy marble in a bowl, or sometimes like a bubble in water. But besides this Bose-Einstein condensate, in every experiment there's inevitably a gas of thermal excitations, thermal atoms. And there's a basic question how the presence of these thermal atoms, and this can be a sizable fraction of the total atom number, will affect the soliton motion, if it will hinder or enhance the soliton motion somehow. So I will start by talking about, by giving an introduction to this and talking about excitations in Bose-Einstein condensates. And then I will give a brief argument why we would not expect that precisely this hindering of the soliton motion appears in certain classes of Bose-Einstein condensates in one-dimensional traps. So there's a classical no-go theorem that forbids the classical soliton friction, so friction force which depends on the velocity of the soliton, like in a damped harmonic oscillator. And this motivated us to present a derivation of soliton motion coupled to thermal excitations from first principles. And it turns out that rather miraculously there's a different type of friction that emerges that is very similar to the friction that an accelerated charge experiences in electrodynamics that could be observed in these experiments on Bose-Einstein condensates. Yeah, so as an introduction, just to kind of set the theme of this talk, I will be talking about Bose-Einstein condensates, and the great things about Bose quantum gases is that on the one hand experimentalists are able to exploit the microscopic properties of atomic level structure and interactions in order to trap them in optical traps and cool them to extremely low temperature. But the resulting system is very appealing because it's universal. So the description of the system is that of an interacting many-particle system that does not make reference to the microscopic details of atomic levels and so on. So the way we describe this is typically by a Lagrangian of this type with a bosonic field operator. It's the theory of a non-relativistic gas of atoms with an atomic mass. They are bosons in this case. And also the interaction itself is universal and described by this quartic contact interaction term. And the nice thing about cold atoms is, of course, that the strength of this interaction can be tuned by means of an external magnetic field exploiting Feshbach resonance, which we have already heard about in the first talk. And of course, as this gas of atoms is cooled to smaller and smaller temperature, at some point we will see effects beyond classical physics. So we will see differences between Bose-Einstein statistics and Maxwell-Boltzmann statistics, for example. And at some point there will be a transition temperature where there's a macroscopic occupation of a single quantum state, which is populated by a sizable or macroscopic fraction of the total particle number. And typically the way this is described is by expanding the field operators in our Lagrangian to leading order, which describes the condensate wave function, which solves this Gross-Witter-Jewski equation. This is a nonlinear Schrödinger equation which contains its own density as a potential term. So for a positive repulsive interaction strength, this potential term will seek to expel atoms from regions of high density. If we're in an attractive regime, then what this will do is to provide a force that allows atoms to aggregate in regions of high density or high condensate density. So if you want to go beyond this and describe excitations or thermal excitations, we expand classically in normal modes around this Gross-Witter-Jewski solution. And formally this is done by expanding to quadratic order in this fluctuation. And the energy eigenvalues of this Bogoliubov-de Gennes kernel give us eigenstates. If we quantize this theory, we can describe the gas as a Bose-Einstein condensate and non-interacting excitations. And the example that we all know about is, of course, the repulsive Bose gas, where this gives rise to the standard Bogoliubov dispersion with a long wavelength linear phonon part, which goes over into a free particle part. So these things can be measured by experiments that induce a transfer of particles from the condensate into an excited state by imparting some energy and momentum onto the system. And yeah, this is, of course, from superfluid helium. We're all familiar with the excitation spectrum of phonon and proton spectrum. So what I will be talking about is Bose-Einstein condensates in one-dimensional traps. So these are created experimentally by confining a gas in a cigar-shaped trap, where the confinement in the transverse direction is very strong compared to the confinement in the longitudinal direction. In this case, the wave function of the system factorizes into a transverse harmonic oscillator state described in the lowest energy oscillator state of a transverse wave function, and the longitudinal, effectively one-dimensional wave function, which solves the Gross-Pitaevsky equation. If you consider an attractive gas, then what can happen in a special situation of one dimension is that the dispersive force by the kinetic term, which seeks to delocalize a wave packet, is counteracted or exactly compensated for by the attractive Gross-Pitaevsky term, which seeks to localize atoms in regions of high density. And what we get is a Gross-Pitaevsky wave function, which takes the form of this inverse Koch form, which is localized around the center position, x, and has a characteristic width of set by the coherence length. The density of the condensate looks like this. So it's a localized lump of atoms at one place in, for example, a trap or on a line. Yeah, and these, of course, they can be created experimentally. So the first one now dating back almost 15 years for solitons. So trains of solitons were created in attractive Bose-Einstein condensate and harmonic one-dimensional traps. And the property of a soliton is that they retain their shape under motion. And also as they collide, they will emerge from this collision unperturbed and retain their solitonic shape. So as oscillations in harmonic trap, a study of these solitons will behave like a classical particle with an effective mass, which is just the sum of all the masses of the individual atoms that participate in the condensate. So it's a very heavy particle by these atomic standards. And if we describe this through an equation of motion, and the force of this heavy particle is described by a restoring force provided, for example, by a trap, which would be a linear force that acts to the trap center. And possibly, if this soliton motion is damped as a function of time, there can be a friction force. And the typical way we think about friction force is this ohmic type of friction, where we have like a damped harmonic oscillator, where the friction is proportional to the velocity of the soliton. Similar, this is called ohmic because it's exactly the type of friction that arises for electrons scattering of impurities in a metal, where gamma is related to inverse scattering time. And intuitively, and we would like to understand, intuitively we would expect that this friction force or this restoring force comes about by interactions of the soliton with its surrounding thermal excitation. And in order to understand this a bit better, we have to look at excitations in this bright soliton background. So it turns out, so in one dimension, the dispersion of excitation is characterized by a momentum state, which is an asymptotic ingoing or outgoing momentum of the excitation. And since the soliton is bound in this droplet, or the Bose-Einstein condensate is bound in this droplet form, there is a minimum excitation energy in this case that needs to be overcome in order to excite quasi-particle excitations. And the way we think about these excitations in one dimension is as scattering states, where we have an ingoing, where the wave function of these Bogoliubov excitations can be written as an ingoing state with a certain momentum that scatters on the soliton potential, which enters into the Bogoliubov-de Gennes equation as a potential term, and then is either transmitted or another part is reflected. And of course, we conserve the probability so that the sum of the magnitudes squares of these things is unity.
I have one question. So you basically say that this minimum energy is much smaller than each for omega perpendicular.
Yes. Yeah.
So you're in a limit where you're very far away from the maximum number of atoms in this soliton. The bright soliton you can have because
where I'm in a tightly one-dimensional limit, so I neglect any effects of.
Yeah, but you know, the second dimension you always see.
I will come to this.
You cannot ignore it.
But I will come to this. I will discuss this. It cannot be ignored, but there's a parametric suppression between this as you make the trap frequency, the transverse trap frequency smaller and smaller. And there will be a different effect, which we argue is of the same order of magnitude as the transverse trap effect. But if you consider this purely one-dimensional system, then I'm free to, of course, talk about these scattering solutions. You can take into account the effect of transverse trapping frequency. I will do so later. But if in this one-dimensional system we think about this as a heavy particle which interacts in some classical form with the surrounding atoms, then what can happen is that these atoms scatter off the soliton profile. They change their momentum by 2k as they scatter, and as they are reflected from the soliton, there's an effective momentum transfer to the soliton. So if the soliton is at rest, we would expect that the flux of particles coming from the left and the right-hand side is equal. So the mean position of the soliton will not be changed, but there will be some jittery motion, some diffusion of the soliton position over time. And likewise, if the soliton is moving, then we would expect that the flux of particles that go in the opposite direction of the soliton motion is much larger compared to the flux of particles that overtake the soliton. So there's an effective friction force provided by the scattering of these Bogoliubov excitations, which are present in this thermal system. So if we formalize this, then we can look up Landau-Lifshitz and discuss the Brownian motion of a soliton in this environment. It turns out we can write down a Fokker-Planck equation for the probability or distribution of the velocity of the soliton. And it turns out that this involves some form with the reflection coefficient, naturally. The caveat in this, why this does not work and why this type of friction should be absent in the system, is that this soliton has a very specific structure. So it forms what is known as a reflectionless potential of Bogoliubov excitation. So as we do this, we can solve for this scattering state analytically. We will find that the transmission coefficient has unit amplitude. So the only thing that will change is that the particle scatters across the soliton potential and then picks up a phase factor here, but there is no reflected component. So the soliton appears effectively transparent to its surroundings. And this is why this ohmic or classical friction, as it's sometimes called, is absent. So there will be no, by this argument, there will be no friction force in the sense that we have in a damped harmonic oscillator, which is proportional to the soliton velocity. There is, of course, a caveat in that we're never in this strictly one-dimensional limit, and we are sensitive to the effect of transverse confinement. We have to take this into account in some form, and this was done, and this will provide some form of classical friction in the sense that I've just described above, because these contribute terms to our effective soliton equation, or the Gross-Petajewski equation, which will break integrability. For example, we need to take into account that these fields are never really in this strictly one-dimensional lowest orbital harmonic oscillator levels, but there are processes where we have some virtual excitations to higher level of the transverse confinement. This will contribute a term that breaks integrability explicitly, and if this is then taken into account, for example, by Joachim Brand for bright solitons and Schlapnikov for dark solitons, this will give an effective friction force which depends on the parameters of the transverse confinement. But the motivation for our work was a bit different. So we wanted to return to this pristine one-dimensional model where we know from soliton theory that friction should not be possible, and asked if there is some residual or different type of friction that emerges due to the interaction with the thermal quasi-particle, because it seems a bit counterintuitive that there should be no interaction whatsoever with the thermal atoms. To this end, I'd like to return to the discussion of the Bogoliubov excitation. So on the one hand, we have these scattering solutions which come with a finite energy in order to excite them from the Bose-Einstein condensate and have propagating states. But there are two solutions or two excitation energies that come with zero energy. So these are associated with these three parameters of the soliton profile. On the one hand, we have a phase. And since the soliton itself enters as a potential term only in its density or condensate density, this phase does not matter for the soliton solution. It's an independent parameter. Likewise, the position of the soliton, if you place it on a line, will not enter. So we can easily transform it out, and the position of the soliton at some place x and y is completely equivalent in terms of the ground state energy of the system. So what we have is not just one soliton in our description, but we have a very large degeneracy of ground states or soliton states, which differ by a phase rotation and a translation of the soliton center. And then there is an inherent problem with the typical quantization procedure, the description of normal modes around the solution that is well known. It's known how I just sketched how to overcome it. We can no longer think of this as some small excitation, which is pictographically shown here as some something that increases the energy around the classical solution, but it's something that keeps the energy constant as we vary this. So we can no longer think of this as a small excitation because this excitation energy is zero, so there's nothing that hinders us in our effective description to have large translation of the soliton or large phase rotations. Now, on the formal level, if we maintain and expand our Bogoliubov field around these zero modes with a small amplitude, we will get various inconsistencies. And the way to fix this, which introduces a collective description of the soliton parameters, is to promote these parameters which induce a zero mode to dynamical variables. So we promote the position of the soliton, which is just a constant here, to a dynamical variable which can depend on time. And likewise, we can promote the phase of the soliton to a dynamical variable. And if we do this in this form, so we have some independent variable here and some perturbation of the Bogoliubov states, which also, the solution of which also depends on the collective soliton variable. And this is a formal way to, on a microscopic level, introduce a coupling between the soliton velocity, so this thing here, and the Bogoliubov quasi-particles. So the effective Lagrangian, if expanded to quadratic order, gives us this bit. This is a part that just describes the excitations of non-interacting Bogoliubov states with some dispersion that I've shown on the previous slides. And then there is a term which gives a soliton velocity or a soliton mass. So this was considered a long time ago already by like Levenstein and Yu in the mid-90s in this context of quantum gases. And for dark solitons more recently by Tsiamara. It means that there has some interesting implication. For example, it implies a diffusion of the phase coordinate of the soliton over time or diffusion of the phase correlator over time. But it's still on a quadratic level. If we, however, take this into account, then this time derivative will act on this and allows us to couple the soliton velocity to Bogoliubov quasi-particles. So beyond leading order, we obtain a term that looks like this, which introduces a coupling between the soliton velocity and the Bogoliubov excitations. So this is the nice thing about this theory. Since it's integral, we can just compute all these coefficients analytically, which I will not present here. But the interpretation here is that we have, if we denote the velocity by some wavy line and the Bogoliubov excitations in and out going by straight lines, then the diagonal terms will describe a scattering event of the quasi-particles of the solitons, and the off-diagonal terms will describe events where two Bogoliubov particles are absorbed by the soliton, increase the particle number by 2, or decrease the particle number by 2 by emitting 2 particles in the continuum. And different from the previous argument, this does not require that the scattering event flips the momentum by 2k. This is something where the momentum can be arbitrary. It can go in with one momentum k and go out with a different momentum k prime. Because of integrability, the matrix element where we have the spec scattering event is suppressed. So we recover this, but we have something more general on a quantum mechanical level that gives us a scattering event where part of the momentum or energy of a quasi-particle is transferred to the soliton, which is then changes in terms its energy and momentum.
These are 3 feet vertices, or is that?
Yes. So you need an interaction.
Yeah, but it's not in 584, it's in 510. You write down the diagram?
No, so the diagrams here just means that this is the soliton velocity, so this would be the x prime or the coupling to the soliton. And these are just your Bogoliubov excitation. I don't know if that would be described. No, that's the beauty of it. This gives you some microscopic way of introducing the soliton velocity as a dynamical variable into your microscopic theory. This is how we capture the soliton motion. And so what we have now on a microscopic level is something that is very well known in physics and familiar from things like the Caldera-Leggett model, for example, where we have a system in our case that's a soliton, and some coupling, this is the emission or scattering of quasi-particles to a bath, which is provided by these Bogoliubov excitations. And our task is to derive an effective equation of motion that does no longer make any reference to the Bogoliubov degrees of freedom. So in some sense, we want to get an effective theory that integrates out the Bogoliubov excitation. Since experimentally we do not have access to the properties of the Bogoliubov quasi-particles, we can, for example, measure the soliton position as a function of time. We can measure its oscillation frequency and its damping. The way this is done was originally outlined by Feynman and Vernon. There are many ways to do it. One way to do this is using Keldysh theory, which we did. Pictographically, it consists of integrating out repeated scattering events where the soliton at some point scatters a quasi-particle and then scatters another quasi-particle at a lighter time. And these correlations between these scattering events will induce some effective friction. If we do this and derive an effective equation of motion, so I'm skipping, of course, the details here, we get something that looks like this. So we have a force term, of course, for the soliton, where this is the total mass of all the atoms that constitute the condensate. If we place it in a trap with some potential term, then there's a restoring force due to the trap. The new things that we get, on the one hand, is a stochastic force due to scattering events of the soliton, which is a white noise term with a correlator that we can compute analytically. And we have some type of friction, but it looks different from the friction that we would have in a damped harmonic oscillator. Right? Now this is an integral that involves the velocity of this soliton at every previous time step. So this is a time evolution which does not just make reference on the parameters of the soliton at one instance, so the position, its acceleration, its velocity, but the velocity of the soliton at every previous step in its trajectory. And since this is a non-Markovian type of friction, we can compute these things analytically if we then plug it in and use this in a numerical simulation of the soliton motion in a trap potential. Yeah?
One question is that, so this is an Ohmic dissipation, so what is structural function? So
I have
small frequencies.
Sorry?
At small frequencies.
Well, it will go as omega to the third power. Yeah, I'm just discussing. So if we solve it numerically, otherwise linear would be your ohmic friction, then what we get, so this is the dashed line, would be just motion in a trap. If we solve the full theory, then we get something that's the continuous line, and we get something that very much looks like a damped harmonic oscillator. But there's still a conundrum. We would like to understand this a bit better, because by our previous argument, such a type of friction should be absent in the soliton motion. So we see a change in frequency as well, but we clearly see also this damping effect here. And if we, well, expand this in a local approximation, so make a Markovian approximation, formally if you look at the spectral function of this, expand the spectral function in low frequency and then integrate back, we do not find a contribution that would be proportional to a delta function, which would give rise to this ohmic friction term that we've encountered previously. Instead, what we get, this whole expansion will start with some characteristic timescale that we can compute with the second derivative. If we integrate partially twice, then we get a term in the effective Markovian approximation, which depends on the third derivative of the soliton position. So something that depends on the derivative of the acceleration, so the jerk on the soliton, again with some stochastic force. And this is a very peculiar type of friction. We have an equation of motion which does no longer make reference to, as an initial condition, just the position and its velocity. We have something that involves the third time derivative. And that's a very peculiar object that we encounter in electrodynamics. This is called an Abraham-Lorentz force. In electrodynamics, we have the situation that a charge that is accelerated by some external force will radiate away part of its energy. And because of this power that is radiated away in the electromagnetic field, not all the work done by the external force can be converted into kinetic energy of the charged particle. And effectively, this can be described in terms of a force that counteracts the external force, which is known as the Abraham-Lorentz force. It's a way of taking into account the field that's generated by a moving or accelerated charge on itself. And very famously, this Abraham-Lorentz force contains some causality paradoxes and some problems, which is sometimes interpreted as something that limits the electrodynamic description, calls for something that some quantum description like electrodynamics and so on. So for example, it's possible that when there's a charged particle has some initial velocity, that this velocity blows up to infinity, even when there is no external force. And if we have an external force, the velocity of this particle will depend on the force at a future time scale, so something that violates causality. Here, this is just an effective description of this, and we have none of it since the underlying equation clearly is causal. So the velocity or the evolution of the soliton depends on the time instance prior to time t. And the way to resolve it in order to get some analytic insight in our solution is to use a trick that can be found in Landau-Lifshitz, where this is assumed to be a small correction to the equation of motion. So what is done as an approximation is to plug in the leading order solution, which is just movement in a trap, into this equation, in which case we get a term which depends for motion in the trap. So with a linear restoring force, it's the one we're interested in, we get some effective friction term that involves the square of the longitudinal trap frequency. And if we plug in the number for a thermal gas of Bogoliubov excitations, then very much we get time scales for this effective damping coefficient that is very the same order of magnitude as the time scales for damping that we would get from taking into account effects of transverse confinement. The difference here, of course, is that we take into account that we have a different scaling, so we can change the longitudinal trap frequency in order to distinguish this very subtle new effect associated with the Abraham-Lorentz damping from the more conventional effect due to the explicit breaking of integrability of this nonlinear Schrödinger equation. Yeah, this I'm at the end of this talk. In the summary, there is we can show that there are classical no-go theorems for the absence of soliton friction. A pristine one-dimensional quantum gas can be circumvented. And there's a different type of friction that resembles the Abraham-Lorentz force of an accelerated charge, and which might be observable with current quantum gas experiments. So if this is further interesting to you, we also collaborated with some science journalists in Maryland who wrote up a very nice news story where this is then the marble in a bowl, the soliton oscillation in the trap, and some, well, I guess this is the non-Markovian quantum friction. Okay, thank you.